Okay, good morning all of you. Today we'll see that fourth unit, that is a DC to DC converters. As you know that function of DC to DC converter, or another name for this is a chopper. In the fourth unit we will discuss two topics majorly, DC to DC as well as the AC to AC. Again AC to AC dividing as a AC voltage controller and cyclic controller. We'll see one by one. In this half, there is two halves in this unit. First half is related to DC to DC. DC to DC also called as a choppers. The name for this is a choppers. That is a DC to DC. Means fixed DC to the variable DC. So if you give input as a fixed DC, you can get it as a variable DC. So wherever we required as a variable DC, like a DC drives and all, we can use it. Another thing is, you may be think that phase control rectifiers also will give the DC. Then why we go for as a choppers? In that phase control rectifier, input is a AC supply. Preferably major things, all the supply are AC. But if input is DC like a battery, fuel cells and all solar power, so there phase control rectifiers we cannot use it. We have to use as a choppers only. Otherwise you have to convert it into AC to DC using diode rectifier, and then we have to use it. So that is the phenomenon. Now there is a first thing is introduction, then classifications. There is a majorly based on the voltage levels. We can classify this step down, step up and down. Both is possible in the same chopper. Because in a step down you will get the lower voltages than the supply. Then step up from supply to high voltage. Then you can get it both, depends on our requirement. So next one is a control strategy. What we noticed in the case of phase control rectifier, there also we are using as a control strategy, firing angle control strategy. There we have different control strategy, R triggering, RC triggering, UJT ramp, all these things. And now here, how the output is going to be vary, that is only the control strategy. In case of phase control rectifier, we are varying the alpha now. How alpha is going to be vary using our firing circuit. Similarly, here our case in a chopper side, there is a control strategy delta or a duty ratio. So that is T on by T. So how the delta is going to be vary. So that is the strategy here. For that we are using as a time ratio control and current limit control. Again we have some classifications here. Time ratio control is dividing as a pulse width modulation. Another one is a frequency modulation. These are the two categories. And current limit control, it will be within a limits, whether minimum and maximum. We can decide minimum as well as the maximum. Then our chopper is going to operate only within the minimum and maximum limits. That is the up to that we will see the today's class. And then we have different types based on the quadrant operation, all these things. Class A or a type A to type E chopper. So this is a first quadrant chopper, then two quadrant chopper, and this will be as a first and second quadrant, then first and fourth quadrant, then this will be all four quadrant operation. This total choppers are dividing as a one quadrant converter, another one is a two quadrant converter, and then four quadrant converter. So these are the three types of choppers: one quadrant, two quadrant and four quadrant. And then how the device is going to be turned off, that is a voltage commutated chopper. So normally, as you know that in the phase control rectifier, thyristors are going to be turned off naturally. But if input is DC, then supply will never go to natural zero. So that's why what we have to do, we need to turn off the device forcibly. For that we required as a forced commutation circuit. So that is only thing here. In that one of the technique they mentioned, voltage commutated chopper, how the device is going to be turned off using the capacitor voltage and all. That is an impulse commutation or a voltage commutation. And there is a regulators are given here, three regulators. One is a buck regulator, boost and buck boost regulator. So all the three step down, step up and down fashion only. So this also we will discuss. Up to now it will be in the half of the fourth unit. Then another part is a two more topics are there in the next part. That is a AC to AC. AC to AC is dividing as a one is a voltage control device, that is we can say that AC voltage controller. Another one is a cyclic converter, that is nothing but a frequency variation. So these are the two things we need to discuss after this. So now we'll see introduction. As you are aware that chopper is nothing but it is a static device like a switch, nothing more than that, only controlling the switch, how much duration it is going to be turned on and how much duration it is going to be turned off. So all the things is only by doing the on and off intervals, that's all. So now suppose if you turn on the device, then what will happen? You will get some output, and again you can turn off the device, then output will be zero, like that. But regular interval, if you do that on process and off process continuously, depends on our requirement of the output voltage, how much duration you need to turn on and how much duration you need to turn off. So all the things depends on your output voltage requirement. Now in this also just variation of the output voltage by switch. That switch is not ordinary switch, it is a controllable switch. That is nothing but a DC to DC converter. So in a transformer, as you know that AC output voltage is going to be vary. But now in a DC case, we can able to get it as a variable voltage through chopper. Before chopper also we have some of the phenomena to get variable DC voltages. We'll see that and why we are going for chopper and what are the drawbacks in the previous conventional methods, and that is the reason to overcome the drawbacks we are going to be used as a chopper. So that also we'll discuss. Now for that step up chopper and step down chopper, all these things will be there. This will be high speed connect and disconnect like on and switch, but the switching frequency are very fast rate we are using to turn on and turn off the device. So the switch will be there in between the source and load. We are operating the switch very high frequency operation, and then we will get it as a average output voltage is going to be controllable. This will be used in the DC drive applications, then electric cars and conversion of wind and solar energies. For that application, we can use as a choppers. That's what I mentioned here, electric cars and wind and solar conversion and DC motor regulation. Once if you control the voltage of a DC motor, obviously speed is going to be controlled. Airplanes and then spaceships and some of the power appliances we can use this. And in general, chopper circuit used for power supplies in computers and commercial electronics and electronic instruments. For all these areas we can use as a choppers. Now you can see the classifications of a chopper. There is a lot of classification, but depends on category. Now suppose if I consider as a voltage, then what are the classifications we can mention? Suppose if we consider as a voltage, then obviously we will represent as a step up and down, up and down. So these are the some of the classes. Suppose if you represent as a quadrant operation, then what I can represent? Class A, B, C, D, E and so on. So up to E, that means E is a 4 quadrant operation. Like that, you will get it as a different classifications. Now you can see voltage level. Based on that, you can see that step down chopper, step up chopper, up and down chopper. Another one according to the direction of output voltage and current. So that is nothing but a quadrant operation. So based on the direction, we can represent as a type of chopper. So now suppose there is a quadrant, let you can consider this one is a current, this one is a voltage. Suppose if the voltage and current both is positive, then it is a type A chopper. And some cases you need only current is negative, then voltage is positive, then this is a type B chopper. And if both is required, then this is we call it as a type C chopper. Type or class both are same. And then another one we will get first and fourth quadrant operation. This is a type D. And all 4 quadrant operation, that will be as a type C. Like this, based on the direction, or you can say that output voltage and current, we can divide as a classification, that is a type A, type B and so on. Or you can say that class A, class B and so on up to class C chopper. This is only the chopper, nothing else. See, there is a you may connect this will be in between source and load, depends on your requirement. Now you can see that in this there is a switch, controllable switch. If you close the switch, suppose there is input some supply, output is some load. That's all, one chopper over. What we are doing, this dotted line, inside the dotted line there is a commutation circuit also will be there. Why commutation circuit is required? Like I mentioned, no, voltage commutated chopper and all. So normally if you use as a thyristor or anything else in this as a switch, but the switch need to turn off sometime and need to turn on sometime, but you can able to turn on once if it is a forward bias and providing the gate signal and all. Once if it is on, then how the device is going to be turn off. That is the major problem in the case of choppers. Once device is turned on, to turn off the device, we required as a commutation. What is that commutation? Here is a forced commutation. Because input is a chopper is nothing but DC to DC, no? If input is a DC, that supply will never go to natural zero. Normally, if it is AC supply means every positive half cycle and negative half cycle, it goes to natural zero. But whereas here, so we can notice that the AC case we are getting like this. So you can able to turn off the device at pi, 2 pi and so on. But irrespective of the time, what is happening? This will be continuously maintained as a constant magnitude. Once the current is passing through the device will never be turned off. So that is the reason we need to apply forced commutation by making use of a commutating circuit. So that is the different in the case of phase control rectifier as well as the choppers. No. So symbol of a chopper is like this. You can use the dotted line represent. It includes device or a controllable switch. In addition to that, as a commutating elements L and C or whatever the commutation circuit we are going to use. So that will be combinedly we call it as a chopper. Now, conventional techniques, as you are aware that in the previously, before chopper, let's consider this is a chopper we are using to turn on and off. By using this on and off, we are able to get as a output voltages. But now, suppose you don't have this facility, chopper is not available, or you can say that olden days, how the DC is going to be variable one. How the DC output is going to be varies, whether it is increasing or decreasing, how the DC is going to be vary. Let's consider Availability also DC. Our available supply is DC supply. Then now it is going to be turn on and turn off. So for that we can see that in the olden days there is a supply and we can use as a rheostat, something like this, and then you'll get some variable point, and this we call it as a V out, this we call it as a V in. So how the voltage is going to be vary now? By varying the resistance value, and then by varying this resistance value, your output is going to be vary. If you keep this point T is here, then what will happen? Total resistance is coming to the picture, your output voltage will be reduced. So you are keep on dropping that resistance, and finally what will happen? If you are adding the resistance, drop will be more. If you are disconnecting the resistance, finally if you connect like this, total output is equal to the input only. By adding something steps, you are getting as a variable output voltage. So what is the drop, or you can say the drawback in this? Waste of energy, because our intention is not to wasting the energy. Our intention is to vary the output voltage, but varying the voltage we are using as a rheostat. Whenever current is passed through the rheostat, then IR drop will be takes place. Then that power loss is going to be takes place if you are using as a resistance. That's what resistance control method. In between source and load, we are connecting as a one resistor. By controlling the value of the resistance, we are able to control the output voltage. So that is the one of the way is available, but it is not a preferable one. Or you can say that potential divider, or whatever you can say, or through rheostat you can able to control. But whatever means that will be as a not suitable one, because simply waste of power. And also another thing, we cannot get the voltage above the input voltage. It is possible only below the rated voltage, from 0 to up to rated voltage, whatever input. Means input, if you give something 30 volts, let assume that your output voltage 0 to 30 only you will get it. Beyond 30 volts it is not possible. So this is the one drawback in this, and power loss is another major drawback, or I can say that. And also it is not that much smooth variation. You may have some steps of resistances, up to that you can get it. It will not be smooth variation. That is the problems. Now another one is a motor generator setup. This is known to you in your EM1 lab. That is, what is this? Magnetizing characteristics of a DC generator, or OCC. This is the experiment we come across in the machine 1 lab, and it is very simple thing. There is a DC motor is there. You can couple that DC motor with some coupling. You can couple the DC motor, and supply is given to the DC machine. Then automatically generator is going to be rotate. Once generate the through this prime mover, if you run this machine, automatically you will get the voltage. And now by varying the field current in the x-axis, you can able to get it as a variable output voltage. So if you vary the resistance of this gradually, automatically your output voltage is going to be vary gradually. But finally, once the core is saturated, you will get the constant voltage after that, irrespective of the field current. Once, even though if you are increasing the field current, this will be constant magnitude. So this is the major problem, but you will get the variable voltage fine. But again, same problems will be arise here. To vary the output voltage, we are using as a motor as well as the generator. Two machines we need to use one thing, and then it will get only up to rated voltage only. Beyond rated voltage, it is not possible. That is one thing. And cost of the setup is high. And also variation, not smoother variation. You can able to get up to the rated voltage only, but lot of setup, motor loss as well as the generator loss, all these things are involved in this. That's why preferably we don't use this type of a control strategy. Another one is AC link chopper. Suppose you may have input is a DC supply. If input is DC, you are using as an inverter. So what is function of inverter? You must remember all the five controllers function. One is phase control, another one is chopper, then AC voltage controller, then cycloconverter, then inverter. So these are the five controllers. So you must remember that five controllers function. Now first one is it will convert DC to AC. Once the DC is available, you are using as inverter, it will get it as a AC. Then we are using as a diode rectifier, it will convert again AC to DC. Our intention is a variable DC. So this one is a constant DC and I required as a variable DC, and through firing angle of the inverter, now here there is a alpha variation is possible in the inverter. By controlling the alpha, you will get it as a variable AC. And if the diode rectifier input is varies, automatically proportional to the output also going to be vary. So that is the reason we can see that what you call it as output variation with variation of the firing angle. So that's the reason you will get the variable DC. But the problem is, you can notice we are using one inverter here and another one is a diode rectifier. So now there is a two controllers we are using to get it as a variable DC. So to get variable DC, we are using as a two controllers. So that is the major problem in this case. So once we are using as a semiconductor devices in a controller, automatically harmonics problem also come into the picture. So that is the problem. And to filter out that harmonics, again we are required as a filters. So we need more filters to filter out the harmonics. So that is the problem. By controlling the output voltage, we are using as a two controllers. So let it be as a semiconductor devices. We are using semiconductor controllers, the inverter as well as the diode rectifier. So this third method or conventional method also not preferable one. And finally, we are using as a chopper. So this is the simple circuit. You can notice whenever your firing pulse is there, then automatically chopper will on or switch will be closed, and no firing pulse means if you remove the firing pulse, then chopper will be off. That means if you are removing the pulse means in turn within a dotted line there is a forced commutated elements like L and C will act and the switch is going to be turned on. So now we'll see that there is a 12 volts input we are giving. Then what is the output voltage waveform if we are able to fire the device? Let it be there is a some duration I turn on the device and some duration off, again on and off. This is your firing pulses, IG. Why IG is required? It is a like a thyristor or any device. We require to pass the signal to turn on the device. When it has to be on and when it has to be off, that decided by the firing pulse. Now I am setting that on pulse as well as the off pulse, again on and off. Now once if we give firing pulse to the this switch during this instant, that I call it as on period, total I call it as a T, means T on plus T off, I call it as a total T. Now once the switch is closed, what is our output across the load? Whatever the switch is closed, current is passing like this, then automatically output is equal to input, 12 volts will get it. So same thing, you make it until pulse is there. So if the pulse is available, this will be on, you will get it as a 12 volts. Now Once this point reaches T on period is over, then what will happen? No firing pulse to the chopper. Then applying forced commutation, the device is going to be turned off. If this is open, then what else output across the load will be the 0. This will be 0. So now you will get it as a 0 volts. Again we are giving firing pulse to the chopper, and again you will get it as a some 12 volts and so on. So whenever pulse is there, it will be on. If pulse is not there, this will be off, and so on. You are getting output voltage waveform will be like this: 0, T on, and this total I call it as a T. Then any instant you want to find the average output voltage, whether it is a phase control rectifier or chopper or anything. To get average output voltage, what you will do is you are integrating one full cycle. What is one full cycle? 1 by T. Integration 0 to T on. Output is Vs or VDC. Whatever notation you want to follow, Vs or VDC is input, you can represent that. Then output is equal to VDC into T on by T. For simplicity, V out is equal to VDC into T on by T is a delta. There the delta is a duty ratio. That is only definition here. Duty ratio is the ratio between turn on time to the total time. That range is 0 to 1, or you can say that 0 to 100% in terms of the percent. So this is the, now we compare with previous conventional methods and this one. I told no, output is VDC into delta. Now we can see that delta is equal to 0. Suppose, then what is V out? 0, and delta is equal to 0.5. What is V out? This V out is equal to 0.5 into VDC. That means VDC by 2. And delta is equal to 1. What is V out? V out is equal to VDC. So you can notice that by changing the delta value, automatically your output voltage is going to be vary, whether it is a 0 or half of the input or up to the input. So variation is there by changing the delta only. How the delta is going to be changed, that is nothing but a control strategies. Now this is clear. So now you can see that input is fixed one and variable output voltage, and this is the firing pulse and then output voltage. Whenever if you give the pulse, we will get the output voltage, and we integrate that portion, you will get it as a this one. Whatever I derived just now, V out is equal to delta into Vs. That is now T, denominator T is there. If you want to represent in the numerator, make it as a F. That F is not a 50H. Remember, don't think that way. Here, F is nothing but a switching frequency. F is nothing but a 1 by T. T is nothing but a T on plus T off. That is the referent. So this is the formula based on the given switching frequency is given something, and turn on time is known. You can easily find what is the output voltage, all these things. Now classifications, we can see other classification, step up, step down and quadrant, all these things I mentioned based on the voltage and based on the quadrant operation. And voltage, you can say that step down, step up, up and down, and then quadrant operation, single quadrant, two quadrant and four quadrant. Again step up and step down. Step down means output will be less than the input, and up means output will be greater than the input, and both is possible in this case. Single quadrant convert choppers type A and type B are the single quadrant, two quadrant type C and type D, and four quadrant operation, it is a type E or class E chopper. So these are the classification. Now we'll see one by one. Step down chopper. What is the step down chopper? Simple circuit. By just notice this circuit. Only thing is to turn on the chopper and turn off the chopper, nothing more than that. So now let's consider if chopper is on. Turn on. What is your output voltage? Current is passing like this. Then current will be rises, output will be same as the input. That's all when chopper is on. So chopper is on, V out is equal to VDC or Vs, both are same. And now current is passing through the diode is a reverse bias. So that's why output is same as the input when chopper is on. Now during that instant, inductor is stored some energy. Let it be plus and minus. Now while chopper is off, what will happen? Inductor polarities will reverse. Now this side is plus and this side is a minus. Then what will happen? The current is passing through plus, it goes to source and it goes to the switch. Now we can see that what will happen? Current is same, but the device, which device is going to be fire if chopper is off? The diode is going to be turn on. So diode is turn on because minus is connected to diode and plus is connected to anode of the diode, then this will be on. If the diode is on, current is passing like this. And then what is the output voltage is equal to 0 because it is a short circuit. That's all the operation, only 2 steps. So first step is chopper is on. Then second step is chopper is off. Chopper is on, output voltage is equal to the Vs. Chopper is off, then the diode, freewheeling diode will be on. Then where output voltage will be 0. Why output voltage is 0? Because the diode is conducting. If this is on, the load is directly short circuited, current will be freewheels through the freewheeling diode. If you want to draw the waveforms also, you can simply draw that supply a DC constant, then firing pulses, then the current waveform and output waveform. So that much easy. You can see that if I want to represent, there is a supply Vs and then I am giving as a some firing pulse. You can give some firing pulse. And you can see on period, then off period, then on period and off period and so on. This is a pulse. Then what is output? Whenever pulse is on, then output same as the input. Then pulse is off, output is 0, pulse is on, output. This is your VDC over V out. Then what about current? What will happen? There is inductor, stores some energy and it rises during on condition. During off condition, this will be plus, this will be minus. The energy, whatever it is stored in that, it is going to be dissipated. So like this, and then again on, again off, like this. So this is the current. Start with minimum, it goes to the maximum, then minimum, like this. That's all. Then why we call it as a step down chopper? So that is the question. Now this is your output voltage. Once if you know the output voltage, what you can do? We can integrate one full cycle. What is the full cycle? This is on period T on. This is a total T this time. And then one full cycle means 1 by T. Whereas in phase control rectifier, what you are doing? 1 by 2 pi. That is one full cycle. Now here is a T is a full cycle. That's why 1 by T. What is integration? Where it is started? It started at 0. When it is ended? Up to T on. So therefore integral 0 to T on. What is your output? Here output is same as the input when chopper is on. That's why we make it Ps into dt plus. What is the next interval? 0, this T on to T. So then T on to T. What is output? 0 into dt. If you integrate this, Vs into T on by T, that is nothing but a Vs into delta. That is nothing but a V out. Now, so now we can see that delta is varies automatically, our output is going to be controlled like what I shown previous, that and these are same. Just this is a normal directly as a step down chopper. There I used only switch to operate how the chopper is going to be operated. Now the range of delta as mentioned 0 to 1. Now put delta is 0 and delta is 1. You will get it as a 0 to Vs is your variation. Output variation is nothing but a 0 to Vs. That is the step down chopper. So now from this we can say that output voltage is varies from 0 to Vs. That's why we call it as a step down chopper, also called as a basic chopper. There is another name for this, is a basic chopper, or you can say that type A chopper. Everything is same, only different names. Type A or class A. These are the different names for this. So that's what given all the waveforms, everything same thing. Chopper is on, chopper is off, current is going to be vary, and the integration. If you want to draw the diode waveform also, you can draw when the diode is going to be on. During chopper is on, diode will be off state. That's why I make it as a 0 here. And if chopper is open, means off, then the energy stored in this is going to be reveals through the diode. That is why we are getting maximum and then it is decreasing. This portion carry by the chopper, this portion carry by the diode. That's what. If you want, you can draw separately also, you can draw. This is this portion and this all the diode, and the rising portions are all the choppers. Now derivation, as I mentioned you, this is the V out is equal to VDC into delta, and or else we can say that if it is RMS, how will you get the RMS? Same expression, the just square it and root it. That will give as a RMS. So this will give RMS output voltage V out is equal to VDC into delta. RMS output voltage of a chopper V out, that is VDC into root del, and average is nothing but into del, VDC into del. And then output power, power is nothing but V out into I out, or V out square by R. V out is nothing but VDC into root del, or you can see that I mean that is VRMS. You can make use of this, you can remove the root because it is not RMS. Now you can see here V out square in that is nothing but you can see here VDC into delta. Yeah, same thing, V out RMS. You can make use of square. So root delta square means delta into VDC square by R. So this is the output power, and then you can see that average output DC voltage is always less than the input voltage. That's why it is a step down chopper. And these are the some of the applications you can use in the DC motors. It is also basic chopper or only motoring operation. Why I call it as a motoring operation? Anybody? Motoring operation in the sense here we can notice that voltage and current is positive. So there is a current and this one is a voltage, and power is a DC. Power DC is a positive. So that means it is a motoring operation. And we'll see that step up chopper. So what is this step up chopper? You can notice this diagram and the previous diagram exactly components are same, only you are arranging the components are different. Earlier this inductor is here and this diode is here and this switch is here for the case of type A chopper. But now for type B chopper, what only or I mean not B, it is a step up chopper, or B also, anyhow that will come later. At moment we can see that the device arrangement is different. Now the operation again say, what is the operation? If chopper is on, what will happen? And chopper is off, what will happen? Anybody can analyze this circuit very simple way. If chopper is on, what will happen? You can see that this is closed, then current is passing through inductor. This is plus, this is minus, and means directly inductor is connected parallel with the source. Therefore what will happen? Inductor will store some energy and current is also passing through the diode and it goes to the load. Output is equal to same as the source. That is the case of whenever chopper is equal to turn on. And now if chopper is off, if chopper is off, earlier there is a this side is a plus, this is minus, it is stored. Now when the chopper is off, this is a plus, this one is a minus. Then what will happen? there is a Vs, stored energy L di by dt, and that will force to the load side. Then the output voltage is equal to Vs plus L di by dt. It is a more than the source voltage. That's why it is a step up chopper. So that also you can derive through derivation mathematically. Only two steps as I told. When the chopper is on, inductor will store energy, and chopper is off, the inductor will release that energy through source and inductor diode to the load. So when the chopper is off state, the source side voltage is more than the load side voltage. That's why that will be connected to the load. That the case we can call it as output here is equal to, our output is equal to Vs plus LdI by dt, that is more than the source voltage. So that is the reason you can say it is a step up chopper. Now when the chopper is on, what is the energy stored in inductor? Anybody? Power into time, that will give as energy. So Wi, what I can write? W in during on condition, that is time is on. Then what is the voltage? Let it be Vs is supply, current is Is. This is the energy stored in inductor. When the energy released by the inductor, that will be during off state. Then what will happen? In this case, you can see the voltage across this, that is nothing but a Vs minus Vout. So let it be output minus input, that is the voltage across the inductor. Current is equal to Is. Then we can say the time is T off. So and let consider these two are lossless system. If system is lossless, then what I can write? V in is equal to, or W in is equal to W out. Then you can equate it, you will get it as a one relation. So that relation we call it as a input output relation with respect to the delta. So now we'll see that chopper is on, inductor will store energy, chopper is off, inductor will release the energy through diode. Now that's whatever I explained theory part here, that I just given some statement. Now we'll see the derivation part. Energy stored in inductor, input, source current, then during on condition. So that's why energy stored in inductor. So energy released by the inductor across the inductor voltage, here output is more, so then minus input, that will give as a Vout minus VDC into Is into T off. Now you just equate these two, as I told, no, once power loss is negligible, or you can say that input is equal to output, that is equal to Wi is equal to W out. So what will happen? VDC Is T on, that is equal to V out minus VDC into Is into T off. Is get cancelled. From this I want V out. So V out is equal to VDC by 1 minus delta. How this will be obtained? By simplifying this notation and divide both sides by T on, all these things. So things will get it as a V out is equal to VDC by 1 minus delta. Or you can see that I mentioned that also. So you can see that V out is equal to VDC into T on plus T off by T off. Then T on plus T off is nothing but a T. So T off I can write T minus T on, and both side divide by T. Numerator and denominator divided by T. Then what will happen? V out is equal to VDC into 1 by 1 minus T on by T. So T on by T is nothing but a delta. So that is only a point here. You can see that you are dividing both sides by T here, by T here, by T here. Then what will happen? T by T is 1 by 1 minus T on by T, that is equal to delta. So therefore you will get it as a output voltage is nothing but a this one. So when we compare the previous one, in the previous output voltage is a step down chopper, V out is equal to VDC into delta. This is the case of step down, and this is the case of step up. Whether it is a step up or not, you identify that first. So again delta range is equal to 0 to 1. If I substitute delta is equal to 0, what is your output? Delta is equal to 0, your output is equal to VDC, and delta is equal to 0.5. Then what will happen? VDC by 1 minus 0.5 means 0.5 denominator. That is nothing but a 2 VDC. And keep on change the delta, and if delta is equal to 1, then what will happen? 1 minus 1, that means 0, means infinity. Then your output voltage will be infinity. So that shows output voltage varies from VDC to infinity. But whereas here in this case output voltage varies from 0 to VDC, and whereas other case VDC to infinity. So this is the difference of step up and step down choppers. Now we'll see the up and down. Again same thing. What the observation? Again three components only. Now once you can see that chopper, and now these two are interchange. You can see that diode in this fashion we connected. Here in the up and down chopper you will get it as a negative voltage also. You can see this, there is a in between or parallelly we are connecting as inductor. Again operation is same when the chopper is on and chopper is off. If chopper is on, what will happen? If chopper is on, you can see that inductor is going to be store the energy. So this is the current direction. Now this one is a plus, this one is a minus. Then what about the diode? Diode will be reverse bias. That's why it won't be turn on. Then output voltage is 0 when chopper is on, but inductor is going to be store the energy. After that, when chopper is open, if this is open, whatever energy stored in inductor, earlier it was upper is plus, lower is minus. No, now it become minus and this will be plus. Then what will happen? Diode will be forward bias because minus is connected to cathode, plus is connected to anode, current is passing like this. Then it is a minus sign. So therefore we can represent it is a negative voltage. Now again same thing we will see this. When chopper is on, what will happen? Inductor will store energy with these polarities, and chopper is off, the current is passing through this diode and it is opposition direction of reference. That's why we call it as a what you call it as negative voltage will be obtained. So now we can see that derivation part also. After that we'll compare all the three derivations. Now, so this theory as usual, when it step up as well as step down it is possible, and when chopper is on, energy stored in inductor, and then chopper is off, so current is passing through the inductor and then chopper, and when switch is off during off time, current is passing through the inductor to the 0 voltage across the inductor. So now you just see this derivation part. Energy stored in inductor in this case as usual of previous one only, VDC IS into T on. And now once chopper is off, what will happen? Inductor is in parallel. Now what will happen? This voltage is equal to the output voltage because chopper is open in this side. This won't get any voltage from the source. Then inductor voltage is equal to the output voltage. That's why W out is equal to what I can write. There is a V out into IS into T off. Now equate this. W in is equal to W out. So IS will get cancelled out, and again simplification is going to takes place. V out is equal to, from this what I can write, you can see that V out is equal to VDC into T on by T off. So V out, you can see this. So there is a V out is equal to VDC into T on by, you can see represent both sides by T. Then what will happen? Again same notation will get if we represent T here and by T here and here also T, then T on by T is a delta and T by T is a 1 and T on by T is a delta. So now from this we can see that your output voltage waveform is like this. I mean expression. In that if delta is equal to 0 to 0.5, you can put delta is 0, output is 0. Delta is 0.5, numerator, denominator will get cancelled, you will get it as a VDC. Now you can see delta is equal to 0, your output is equal to 0. Delta is 0.5, then what is your output? Is equal to VDC, and delta is equal to 1. then your output is equal to denominator 1 minus 1 0, so output will be infinite. That means as we see that, as seen that in the previous step down chopper 0 to VDC, we call it as a step down, and VDC to infinity we call it as a step up. That only I mentioned here. Delta value 0 to 0.5 it is a step down, 0.5 to 1 it is a step up, and this is the case we are able to get it same chopper, we can get it as a step up as well as the step down. Now we can see that control strategies of a chopper. So what is the control strategy? How the delta is going to be vary? As now we discussed one thing. What we discussed is for step down, V out is equal to VDC into delta, and step up case V out is equal to VDC by 1 minus delta. Up and down, this V out is equal to VDC into delta by 1 minus delta. So now for all these, what is the control parameter here? This is a delta, whether it is up or down or step up and step down. So how the delta is going to be vary, that is only the question. And delta we can see that T on by T. This is the notation. Whatever means you want to do delta, that we can able to change the T on or T, or otherwise this I can write T on by T is nothing but a T on plus T off. So therefore we can able to control the delta by controlling the on period or by controlling the off period. So there is a two ways will be there. Once we can see that if the delta is going to be controlled either T on or a T off, both sides. Suppose if it is a constant frequency means what? T will be remains in the constant. You keep T will be constant and change the T on, because T is nothing but a T on plus T off. Now suppose if I keep T on, then what will happen? Any one has to be changed. So T off will be changed, T will be changed. But now my question is, you keep T will be constant. If this is constant, what is possible option according to formula? Only T on. You can control the T on, automatically delta is going to be controlled. T on by T now, T keep constant and keep on changing the T on period, automatically it is proportional to the delta. Therefore delta is going to be control. Similarly, that is one way. Other way is I can do other version also. T on by T is nothing but a T on plus T off. I fix the T on, not capital T. I fix the T on. If I fix the T on, to change the delta, what is possible option I have? Only T off. You vary the T off. Different values of T off, you will get it as a different values of delta. That is one. Second one. You can see first one is keeping delta constant. This is delta constant. Keep on vary the T on. You will get it as a variable delta. That is first. This is second. Third way also is possible. Delta is equal to same T on by T on plus T off. Now you fix the T off. You fix the T off and you vary the T on. Then also delta is going to be controlled. So these are the possible options. I will show that waveforms also. Now these are the control strategies. Two control strategy. One is time ratio control. Another one is a current limit control. Time ratio control dividing as a pulse width modulation means constant frequency. Constant frequency means T will be remains constant. Variable frequency T is going to be vary. If any one is fixed, other one is varies, total T will be vary. No, total T vary means frequency is going to be vary. And then current limit control within a limit, I minimum and I maximum. Now first we will see the frequency modulation. Now what is the value of delta here, anybody? Let us assume that I made it T on is this much duration and T off is this much, total T is there. Then what is the delta? I can write delta is equal to T on by total T, or I can say that on period I made it 1/4 of the total time. then the delta is equal to 25%. See that comparatively total T on period I consider 25% as of the total T. Then you get delta is 25%. Now I want other delta value or 50 or maybe 75%, something like. Then what is possible option? You don't change the total duration of a T. T on plus T off must be same. You cannot change. So that is the reason you can see that T on is let's consider here is a something 100. This will be 300. Then total is a 400. But keep total 400. Then I want to change the delta. Then you can keep on period is a 300. Off period is a 100 milliseconds of time. Then the total time remains constant like that. Then what will happen? Delta. Delta will increase. So like this, you can able to control the period. Now you can see that on period. Let in this case consider T on 3/4 of the total time. Then delta is equal to 75%. Here T on is equal to 1/4 of the total time. Delta is equal to 25%. So like this. This control strategy we call it as a time ratio control, and constant, because we are ratio is time only. That's why time ratio control. But we are keeping the frequency is constant. You can see that time is constant, therefore frequencies remains the constant, so that we don't affect anything in this case. We are keep on changing the on duration by total fixing the T on. Then if we change the T on, automatically proportionately off also will change. We'll get it as a delta is going to be variable. And then variable frequency control. So what is the variable frequency control? I fix the T on. For both these two cases, you can see this. I fix the T on. This on period and second case on period is fixed. But what I did, off period is varies. This much off period. When now what is the total time for first case? This is a total time. From here to here is the total time. Then delta is equal to, for our T on period, whatever I use, T on, you can see here. So T on, that is equal to 1/4 of the total time, because here is a off period is large, then 25%. Now second case you can see T on, this time durations are same in compared to these two, durations are same, but total time is only small, this much, when earlier total time is this one. Then the T on is equal to 3/4 of the total time. Total time only this much, no? In that T on is more. That's why it is a T4. So this is a 75%. And you can see the delta is equal to 0.2 first case, 0.25 second case, 0.75. Now what is the frequency? Frequency is first case is different, second case is different, no? First case is what? Large time. Then frequency will be small. And second case, time is less. That's why frequency is high. Every value of delta, you are going to vary the frequency. That is one way. That means second way. Third way, I told no, off duration is fixed. You keep the off duration fixed and you vary the on duration. Now you can see that both cases off durations are same, but here on duration is small, but here is on duration is large, and here also you will get it as a variation of the delta. So, but in this phenomena, if you use this way, what will happen? Automatically, problem is, if you are using as a off duration is large, this much large, the current waveform if you draw, this much duration device is completely off, current will reach us to the zero and remains in the zero, there is a discontinuity problem. This will see that current will rise and then it will decrease somewhere and it remains in the zero. So that is a discontinuity problem will be arise if you use as a large off duration, and that is one problem. And other problem, for this value of delta and all the delta values, frequency is going to be changed. Every value of delta frequency is going to be changed. That will be designing of filters is a complicated. You don't know what frequency it is going to be operate, switching frequency. The filtering requirement is required, but the design of filter is a complicated. That's why this method is not a preferable method when compared to the pulse width modulation. This we call it as a frequency modulation. Every case frequency is going to be vary. That's why this we call it as a frequency modulation. And now we see the last one is a current limit control. It is very straightforward. It is very simple, and it never go to as a discontinuity mode of operation. You can see that current waveform. What we want to provide as a firing pulse. Suppose you can see that current is minimum. What it should not be allowed below minimum value. Then what you have to do? You have to give the firing pulse. This is a firing pulse. If the pulse is given, chopper is on, current will be gradually rises. And once it reaches to the maximum, let's see that current is reaches as a maximum. If I am giving firing pulse further, something like this, then what will happen? Current will go beyond the maximum. That's why what I have to do? I have to disconnect the firing pulse. Now I made it as off. Then if off, what will happen? Current will be gradually decreases. Current will be gradually decreases. Again, once the current is minimum, reaches to the minimum, again you have to give the firing pulse. It increases the current. Again, you are disconnecting the firing pulse. Like that, you have to provide a firing pulse. So whenever it reaches to the maximum, then you disconnect the firing pulse. Whenever it reaches to the minimum, provide the firing pulse. And like this, if you provide the firing pulse such a way that your current waveform will be improved. You can see that current is always within the minimum to maximum. Whatever new values you want, you can provide the minimum value and maximum value such a way that you provide the firing pulse. Once it reaches the maximum current, disconnect the firing pulse, reaches to the minimum current, provide the firing pulse, then the chopper is going to be operate within a minimum and a maximum. So this will be used for the motor drives and all. We want to operate within a limits, you can use as a current limit control. So this is this today's class. If you have any doubt, you can ask me. And you can see tomorrow morning, instead of Thursday class, I will take tomorrow morning first hour. You are free on that. Wednesday 9:10 to 10:10 I will take power electronics class. Instead of Thursday 10:20 to 11:20. Your attendance is on Thursday attendance only. I will take on Wednesday. Class is 9:10 to 10:10. Okay, if you have any doubt, you can ask me. Otherwise, you can leave.